So we talked about a process in a not running status versus a running status, but we haven't actually talked about when exactly a process would be created. So a process would be created for different reasons. Of course, based on whatever would be sent from the end user, how would the operating system will decide on creating a process? So operating system will decide on creating a process if there is a new batch job to be created. The operating system at this point will be provided with the batch stream to decide on whether a process will be created or not. Just a second, I lost yeah. And then what else would allow the operating system to create a process? If for some reason there is an interactive login, a user at the terminal logs into the system. Once a user has decided to log into the system, the operating system will immediately create a process. Also, operating system might decide to create a process to provide a certain service, either for the user or the operating system itself. I don't think my camera is on, correct? Can you see me now? Yep. So, and also, if the operating system has received the request to spawning existing processes, sometimes the operating system might decide, due to some circumstance of modularity or parallelization, the operating system would decide to do spawning a process from another process, like creating a process from another process. At this point, we will have a parent process and a child process. So when we see an interactive log into the system, the operating system will create a process. When there is a batch job comes from the end user, then the operating system will create a process. When there is a reason for the operating system to implement a certain service, the operating system would have to create a process. Maybe this is primarily not to allow any extra weight in the system. The operating system itself will create a process that will take part of the ideal process job. So it will help a little bit to reduce the waiting time in the system. Or the operating system might create or spawn a process based on the request of other process. So as you can see, the process creation is related to three main terminologies. The first one is process spawning. The second one is a parent process, and the third concept is a child process. So spawning processes, this is exactly the situation when the operating system create a process at the explicit request of another process. So maybe process one, when it was an execution, it turns out that there is a need for a process one star, like a small process to be created. Then the process one will send a request to the operating system, say, hey, I would need a process to be created right now, which is one of my children. So each process could spawn another processes. And that will be an explicit request from the processes to the operating system. The process that has sent the request is called the parent process, and the process that has been created is called the child process. Once a process is created, keep this in mind, then a process control block will be created and the process will be immediately stored in the RAM. We don't have any hard drive switching now for the current two-state diagram. Once we move to different state diagrams, you will see that some processes might send a request to create a new process, and the new created process might not be even in the RAM. It might be decided to go and reside in the hard drive based on the explicit request of the parent or the request or the strategy of the operating system itself. So we talked about the creation of a process. So similarly, we need to know when exactly a process will be terminated. A process may be terminated due to different reasons. The first one that I would like to share with you is normal completion. The process has started, it has been assigned to the CPU, although it has been in a couple of interruptions maybe, or not even interrupted, but it has been completed in a normal scenario. At this point, the operating system has completed the entire process with no issue. Or a process may be terminated if it takes forever. Like if I send a request to the IO and it stays like for 7 minutes and the operating system does not allow any process to exceed 1 minute of execution, as an example, at this time, the operating system will terminate the process. We don't want to get into what we call the wall clock time, which is the amount of time spent executing And in this case, we will have a lot of interactive processes that will cause a huge extra waiting time in the system. So it has a time, it has exceeded the time limit that was assigned by the operating system. So the operating system will decide on terminating the process. Or maybe we have unavailable memory for this process. So the process would require more memory that the system can actually provide. So the system or the operating system will terminate the process. A lot of reasons that you can see that might cause a process to be terminated. It might have an invalid instruction. It might have data misuse, like try to access a piece of data that is wrong or not even initialized. Maybe the parent termination, the parent process has explicitly requested that the child process would be terminated. So at this point, the parent will, the operating system will terminate all the children, or the parent process itself has completed its own execution and left the system. That means all the children that have been created for such parent process should also be terminated. So we talked about parent request, we talked about parent termination, we talked about invalid instructions, we talked about time overrun, we talked about exceeding time, we talked about any error that might be caused by such a process, whether it's protection related or arithmetic related. We talked about memory unavailability. We talked even about the normal completion. All of these are reasons for terminating a process. When I say terminating, means the process is now out of the system. As we have previously discussed, we talked about only two-state diagram as a queuing model. At this point, we have seen that some processes might send a request for an IO, and it's neither in a not running status or a running status. So they have slightly switched or modified the two-state diagram to come up with a new process model that like closely enough describe different behaviors of the processes within the system. A process could be in a new status. This is when the process is created. So we know that the process is a new state. So we say this process is new. It's still in the memory, but it's new. So this is when the process is created. And then once it has been admitted, that means it is in the queue right now. So we can see it in the queue. So we say the process in the ready status. Once the dispatcher decided to fetch this process for execution by the processor, we say it's in the running status now. Once the process is completed, we say it's in the exit status. That means it has been released from the system or it has been terminated. So it left the system. So a process is terminated, that means the process is in the exit status. However, we might see internal behaviors rather than this regular behavior. What is the internal behavior is a process is created, it was ready, it was dispatched by the dispatcher, it was in running status, and then for some restrictions provided by the operating system, it's still in execution, but it was timed out or interrupted. So it goes back to a ready status, which was the not running status before. Or it has sent an IO request. So now it's not in a ready status anymore. It is in a blocked status. Once it moves from the blocked status, that means it has received a response based on the IO request that it has made. That means the event that was the process was waiting for is now completed. So the process moves from a blocked, not going immediately into the running status. It would go into the ready status. Is this clear? So a process could be ready, going to running, going to exit, or ready, running, back to ready again, if it has timeout or interrupted. Or if it waits for an IO event, it goes to a block status. If the IO event has been completed or the event that the process is waiting for is completed, then it moves from the blocked status to the ready status. And then the entire cycle resumes. This is a slightly explained to the three examples we discussed before. If you remember, this guy starts from address 5000 and we were up to 5006. Remember this? We have 5 instructions in a row, correct, guys? And then what happened after? It was time out, correct? So what is the status of A here? Is it new? Is it ready? Is it ready? Is it running status? Or is it exit status? Or is it block status? What do you think? A in the first part. Amazing. So A here is running status. I'm going to say it's running. Now it has been assigned to the CPU. Now, due to the timeout, Where is A between, I'm going to say this is, sorry, this is address 5000. I'm going to say this is time T1 up to T2, so T3. So T1. From T1 and T2, A was in a running status. What about from T1 to T3? Was it blocked? What, like, do you think A was waiting for an IO event? It was not waiting for IO event. So it should be in what status? It should be in the ready status, correct? Should be on the ready status. 2 T1s. Oh, thank you. So I have to correct this. I'm just like, my Apple Pen is not helping me. So T1 and T2 was in the running status. Between T2 and T3, it was in the ready status. And then between T3 and T4, what do you think? Now we are resuming instructions again for A from 5 and 6 up to 5, 0. I'm going to assume like 12. What do you think from T3 to T4? What happened? What is the status of A now? So you can see it's in ready status, but it's not blocked for any event. Between T3 and T4, what's the status of A? It's running again. And then, what do you think after this? Like here, is it ready status or what? What do you think? Like from T4 to T5. Thank you. So that's exit for me. So this diagram does not reflect exit, but I will add here like this dash, whatever is for exit. So this is exit status. And I'm going to add here this one. It's funny, but it's new status. So before this, A was in a new status, correct? And then it goes into running status, ready status, running again, and then exit. Guys, do you agree on that? Now what about P? What do you think B? B was, what will be the initial status of B? Well, what is the initial status of B? What do you think, guys? Before ready, it is in a new status. Then it goes into ready and then running. And then what's this black area? We don't know exactly when the IO request has been responded. So that's blocked. Perfect. As you can see, the dispatcher switches between running, 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 running. We don't deal with the dispatcher as a process because it's not one of the processes where we have to know the status of it. It has to be running all the time when there is a call or dispatching request to be made from the queue to assign a process to the CPU. So because we don't know for sure, oops. So I think you're talking about this one. So after this one, the last instruction, so this instruction was from 8000, I'm going to say from 8004. The last instruction here is an IO request. So this is an IO request that was given in the example. So that's why after instruction number 8004, A is blocked, right? So this queuing model would be slightly different. How would it be slightly different? If we talked about single queue model versus multiple queue model. A single queue model is we have two queues. One of them is called the ready queue in blue. The other one is blocked queue. What do you think the ready queue is about? What's the ready queue is for? What do you think, guys? What is the ready queue? What is the ready queue? It contains which processes? The processes that has IO request or the processes that has timeout or interrupted? What do you think we should see in the ready queue? Thank you, Nafia. It's all the processes that are ready. Perfect. So they have been already assigned to the CPU, but for some reason they have timeout, as you can see here. So the timeout, all the process from the timeout, it will return back to admission again, going back to the ready queue. And then which process do you think will leave the processor now and will have to wait for here? So I think this option is for A and C. What do you think? Which process would go to the, thank you. So B will go here. In the previous two-state model, we only had one queue, but in this model, we have two queues. The first one is for the ready queue, which contain the processes that has been assigned to the CPU. And for some reason, they have been interrupted. So now they have to go back into the line, their own line, the ready queue, versus adding a new queue, which is the blocked queue that has all the processes that are waiting for an event to happen. the IO request. That's why we have created a blocked queue where all the processes will join this queue until the event occurs, then the process will join the ready queue again for execution. We could look to it as a 2-queue model for ready and blocked queues, just for a single block queue, or we could build multiple queues based on the event. So maybe this is a printer request. Maybe this is a keyboard request. Maybe this is, let's say a different example. Maybe this is a hard disk request. So we could have one queue, one blocked queue for all the events, or we could have multiple queues based on the event type. So at this point, once the event, now previously we were said, just event occurs, go back to the ready queue. Now, no, if event 1 occurs, all the processes that are waiting for the printer will be released. Maybe if the keyboard request occurs, all the processes that has wait, or the process that is waiting in this queue will be released in the order of releasing. And then each one of them will go back and join the ready queue to be well dispatched to the processor. Keep in mind, at this point, we still have the timeout that will take a process from running status to non-running status. So here we are going to the exit status, if you remember, and the admission will only relate it to the new status. Is this clear, guys? What if a process would be suspended? So we talked about ready process. Then it's a way of organizing the processes, and instead of having just one queue for all the events, maybe all the events are not of the same priority, or all the events will not take the same time. So it's better to identify processes based on the event time. It provides better organization and optimization by the operating system due to the type of events that might cause extra delays. So for those events that would need to be of 100-second delay, the operating system would know which process would need 100 seconds delay, because they are in the queue that has all the processes of 100-second delay, as an example. So it's a bit of organization by the operating system to assume that it's not one queue for all the events, it's multiple queues for different events. That's a little bit of design of how the operating system will build its own dispatcher or scheduling mechanism. Now, it is supposed to say part or all, not part of all. Is it a part or Mohammed, I'm not sure which oh, you mean in the slide? Thank you. Part or, thank you. We talked about ready processes. We talked about running processes. We talked about blocked processes. But as a matter of fact, there's another state that we can see a process in. This is when we call it suspended process. Keep in mind, we talked about spawned processes. Spawned processes is a process created based on the request of other process, a parent or child. This one is different. This one is suspended. A new state is a state that the process will take when it has been initially created, but it's not in the queue yet. So it's not in the queue yet. It's just like newly created with the process control block. So a suspended process relates to a concept called swapping. So swapping means that based on a parent request or based on the decision of the operating system, there was a need to swap a process from the memory to the hard disk. We move a process from the memory to the hard disk. When none of the processes, when exactly this happens, why the operating system would decide on swapping a process from the main memory and to the hard disk, this will add a new state to the processes. It's not blocked process anymore, it's a swapped process or suspended status. When none of the processes in the main memory, like assume this is my memory now, and this is process A, and maybe process B in the memory, process C, and a process D. If we check the process control block of each process, and A is not in the ready, A in the blocked status, and B in the blocked status, and C in the blocked status, and D in the blocked status. So all of them are like, it's not in the ready status or not even in the running status. Why I leave them in the memory then? Do you agree? If none of the processes in the main memory is in the ready state, do you think I should keep them in the memory and not using my memory efficient? Or I might swap them out of the memory to the hard disk. Still, I'm keeping tracking of their information, but I'm swapping them out to the hard disk so I could create and invite new processes into the memory and assign them to the CPU. What do you think? Disk like hard drive, yes, like hard disk, the secondary memory. So we have the main memory of the RAM, and we have the secondary memory like the disk or the hard drive. What do you think, guys? Of all the processes in the memory now, when we check the process control block, they are in a block status. Do you think it's wise to leave them in the memory or to swap them out to the hard drive or to the disk? Swap them. That's the decision made by the operating system, either based on a parent request or based on the strategy of the operating system itself. This has happened when we see that all the processes in the main memory are not in the ready status. At this point, the operating system will swap either one or more of these blocked processes out into the disk, and then we'll create a new queue. This queue is called suspended queue. This is a queue of all the processes that have been temporarily kicked out of the main memory, or we call it suspended status. The operating system will bring them back based on, again, on the explicit request of a parent process, or when it's time for the process to return back into the main memory. Or and in addition to this, the operating system, once it decides to swap a process out, put it in a suspended status, it will bring another processes to the system or create another processes in the system, and then honor a new creation of a process. Execution to those processes will be like normal. Once they have returned it back to the main memory, it will be considered as a new process, and then moving forward to the same diagram as we talked before. Keep in mind that swapping, on the other hand, is due to the fact that all the processes in the main memory is blocked. When exactly a process is in the blocked status? Because it waits for an IO request. IO request takes more time, so that's why the operating system would have to be more efficient to decide that these processes are blocking the access of the memory and maybe the CPU, waiting for a status that might not happen soon. So it's time to take it out of the system into the out of the memory into the hard drive, so we allow more efficient use of the resources. Swapping generally will enhance the performance because it guarantees that the utilization of the CPU is high, in addition to the wait time of other processes to join the system to be executed is less. So at this point, we need to revise our state diagram, starting from new state, the same ready state. We had all of these states. Can you see which state now is added to the diagram? Which one is added now to the diagram? Suspended. Do you think ready to suspended or block to suspended? Which edge I should add? Ready to suspended or block to suspended? A process is suspended if it was originally. What do you think? If it was ready or if it was blocked? Blocked. We don't have ready to suspended, and yet it has to be blocked first. The operating system will only decide on suspending a process or swapping the process from the main memory into the hard disk if it was originally blocked, like waiting for an IO. So at this point, it was originally running, event happened, so it's blocked. Some of them would be decided to be suspended or swapped out. So blocked to suspended. If it has been activated back, it would go back to the ready status as if it's similar to a new process. Is this clear? So when we talk about suspended processes, we know that processor is way faster than an IO request because all the processes are waiting for IO while the processor is actually processing many other processes. Swapping these processes to the disk is primarily to free up some memory, as I said before, and also to achieve high utilization of the processor. Now, we would like to think about new concept that will be added. Blocked state becomes suspended when it's swapped to the disk. There are two variations of suspensions. We talked about block going to suspend, or we can even add now ready going to suspend. When exactly a process could be ready and then swapped to suspend status, sorry. What do you think? What do you think? What's new in this diagram? So let's review it together. So a process is new. It will be admitted to the system. It will go to a ready status. It will be dispatched by the dispatcher. It will be in a running status, timeout, go to ready until dispatched again. When it's done, that's a release going to exit. Or what else? It was already new process, and then it goes to a ready status. It was running status, moving backward. That was an event request. The event has put the process into a blocked status. The blocked status means the process is waiting for an event. That means the process, if it's in this status, the process stays in memory, correct? So the process, if it's blocked but still in memory. Blocked suspend mean the process where? What do you think? Where is the process? Where is the process? Hard drive is in the disk. Should we move a process to ready immediately, or we create another queue so we give a chance to differentiate between new processes versus suspended processes? I think it's fair to deal with the suspended processes fairly enough that they were in the system before, correct? So we should not treat them as if they are new. We should treat them as if they were suspended and going to suspend it to be ready before entering the system. That would give them fair treatment compared to the new admission. So at this point, we will split the suspended status into two other status. The first one is block suspended, and the second one is ready suspended. So block suspended means the event happened, but do you think ready suspended is in the memory or in the hard disk? Ready suspended here, what do you think? It's still suspended. It's still suspended, guys. It's still suspended. Thank you. So it's still in the hard drive. When it moves to ready, that means it's where? Is it in the memory or on the hard drive? Thank you. That's what happened. So although it's in the hard disk, but we have to identify that it's not blocked anymore. It's ready status now. So because it's in ready status, we would give it high priority to enter the system compared to a new admitted process, or not high priority, fair treatment compared to new admitted process. So at this point, we will allow a new state to be added to the system that is called ready suspended. It's still suspended, it's not in the memory, it's still in the hard disk, but it's not waiting for any event to happen. It's ready now. Is it clear? And as you can see, even a new link is added. Do you know what's this link? So to take like a big picture of all the behaviors we may expect, we even might see some processes that were in the running status, and for some reason the operating system has decided to move those processes into the hard drive due to priority of others, due to memory inefficient for processes to be used as of now. So the operating system will take from the running status, not going back to the ready status, but we go to the suspended ready status where it's ready, but it's not in the memory anymore, it's on the hard drive. Go to ready suspended, how so? When it was under execution, but it's not because of a timeout, it goes back to a ready status. It's because the operating system decided to suspend the process. The operating system has decided to take the process out of the memory going to the RAM for some reasons. Those reasons might be because there is no memory availability for the process to be executed. The process takes forever, although it's not blocked, but it takes forever. It takes a lot of instructions to be executed while it's not of high priority. So the operating system will switch it back to the hard disk, but it's still in the ready status. So it will have its own lineup when it comes back to the system. Can the process be two states, or is ready suspended one state? Ready suspended, that's ready means it's in the memory and it's ready for execution. Suspended mean it's on the hard disk. Suspended blocked mean it's on the hard disk, but it's waiting for an event. Blocked means it's in the main memory and it's waiting for an event. So you can see one process could be in different states based on where the process is and what's the behavior of the process at this moment of the time. Did I answer your question? So that being said, when a process is created, the operating system has the option either to create it and send it to the hard disk, I don't want to run it as of now on my RAM, or send it directly to the memory. That's why we created the ready suspend status. So as you can see, this is the 8 state diagram. Sorry, that's the 7 state diagram versus what we have discussed before, which is the 6 state diagram. Versus what we have even discussed over here, which would be the 5 state diagram. This is the 5 state diagram. So as you can see, moving forward from the 5 state, we added, compared to the 2 state diagram, we added the block state. Moving to the 6 state diagram, we added the suspended state. Moving to the 8 state diagram, the 7 state diagram, we added the ready suspended and the block suspended state. So assume a new process is created and there is no available memory. Ahmed, there is no available memory for this new process. So the operating system has received a batch request, but we can't find memory enough to allocate the process. Where do you think the operating system would put the process? What do you think, Ahmed? So he has to put it on the hard drive, but it's not blocked. It's not blocked. It's ready. So we call it ready suspended. That's why we might have a ready suspend. So this state is in particular added to observe the fact that the process is not waiting for any event, but it's not on the memory. It's on the hard drive. Status processes get higher priority in the queue. Nafia, it depends on the dispatching system. We would like to be fair enough such that when the process is in the ready suspended, it is treated differently as compared to the new processes. The previous diagram over here, like in the 5 state diagram, treats the new processes over here, and the suspended processes for in the same fashion. Why they should not be the same? The suspended processes was originally in the system. Why it should go back to the ready state, the ready queue, as if it's like the new process? So that's why we have added different queues. Like as you can see here, every time we see, like, if you would like to help me with building a diagram, this is what queue? What do you think? This is what queue? I'm going to say this is the ready queue. Going to the CPU by the dispatcher and then exit. If there is a timeout, where do you think the processes will go? Timeout, I didn't say event, I said timeout. Where the processes should go? Okay, at this point, let me leave it because I will have a little bit of adjustment, sorry. So it should go to the ready queue. Or the process is waiting for an event. When the process is waiting for an event, which queue the process goes to? Assume one queue for now. What's this queue? Blocked queue, perfect. So some of these processes would go from the blocked queue to where? If we decided to suspend them. If some of these processes in the queue should not be in the memory, it should be suspended. Where it should go? Thank you. So we have another queue over here that is blocked and suspended. So now all the processes in this queue, is it in the memory or in the disk? That's in the memory, correct? Blocked, suspended, where is it? Is it in the memory or is it in the disk? Hard disk, perfect. Now event occurs. So this is event occur. Which queue it should go to? Like this is an event, like event occur. Where do you think this queue is? What's this queue? It's still in the disk. So is it ready or is it, thank you. So that's ready. I just want to add it on the top so make it easy for me to write. So that's a queue that is ready. It's ready to go. The event has occurred, but at the same time is not in the main memory. It's suspended. So where this should go next? It's now ready suspended. Once it's out of the hard disk, where should it go? Thank you. So go back to this ready. So this guy has two options. Either it goes directly into the ready status, or it goes into this queue if there is suspending request. So if a process has been assigned to the CPU, the timeout for the process will at this point the decision will be made by the operating system, or I will take it immediately to the ready queue, or I will send it to the ready suspend. It means I will take it to the hard disk. At this point, when a new process arrives, so that's new processes, a new process will go into what queue? Will it go to ready suspend or go to ready? So now we have new process arriving. What do you think? Go to ready? Thank you, Ahmed. So it go to both. So it could be going to ready status or it could be going to ready suspend. That's primarily based on the request of the operating system, based on the memory availability. Now see if it's based on the scheduling mechanism, the strategy of the operating system, but the idea is we are expecting different behaviors of processes, and the decision where it goes, it's mainly primarily to the dispatcher. But as you can see, we add more queues, we add more states to identify the processes. When exactly a process will be assigned to a ready queue versus a suspended ready queue, it's the sole or discrimination of the operating system to make such a decision based on all the resources availability. As we studied this course, we don't know exactly how this internally happens. It's more into the optimization that the operating system will do to do such assignment. But conceptually, we know that a process, when it arrives, if there is no event to wait for, the memory is available, then it goes immediately to the ready queue. If there is no memory available, but it's ready, it does not wait for any event, it goes to the ready suspend on the hard disk. It's still ready, but it's on the hard disk. And then if a process joined the ready, and then for some reason it goes to the CPU and it's waiting for an event to happen, then I will take it to the blocked queue. If the operating system decided to move it from the blocked queue to the hard disk, this is for a sole request by the operating system or a parent process that we need to free some memory. The reason for suspending a process or swapping a process from the main memory to the hard disk is because we would like to free some space of the main memory. Event to happen for a process to go to block. So a process would go for a block if it has an I/O request. What's an I/O request? A request to access input devices or output devices. Output devices like screen, monitor, input devices like keyboard, for example. Output device could be a printer. Output device could be whatever, a scanner. So these are requests for input-output devices. A process will go into a block status if there is an I/O request. Prioritize, perfect. Nassif, we will talk later about memory optimization. As of now, we are talking about how the process manager works. When it receives multiple processes, each one of them with different status, each one of them with different requests. How the process manager would work, there's a lot of queues that are created to align with the behavior of the processes. We know the baseline of the behaviors, but we don't know internally what will happen because that's the decision made by the operating system based on what the resources, availability of resources are. So I/O request, no, Davis, I/O request does not take any space on the memory. The process itself is ideal, and if there is many processes that would need an I/O request, that means all the processes themselves are occupying a space on the memory while they are not in execution. Then why I should leave them in the memory? I can take them out into the hard drive. Is it clear? All right, Ahmed, a process, a job, as I said previously, if it has been scheduled to be executed, then this job could be one process or multiple processes. So a job will be a process in the running state if it is assigned to the CPU. Yeah, being used by the processor. So few things we need to know about the characteristics of a suspended process. What is the main characteristic of a suspended process? A suspended process is not immediately available for execution. It's on the hard disk. So if it has to be available for execution, we have to move it from suspended blocked into a ready status. So, and then it's still on the hard disk. If you would like to move it back to the memory, we move from ready suspended to a ready status. Also, the process itself may or may not be waiting for an event. So if we have blocked suspended, and if we have ready suspend. Which one is waiting for an event? The first one or the second one? Block suspend or ready suspend? What do you think? The first one. So that means it's on the hard disk and waiting for an event. That means it's on the hard disk, but it's not waiting for an event. So the process is placed in a certain suspension status. This is by an agent. It could be by itself due to the request made by the operating system or management signal between the operating system and the process. It could be based on a sole request of a parent process that decided that this process has to be suspended, or it could be even by the operating system internal management that has decided to move the process for suspension status and preventing the execution of the process to efficiently managing the resources. So until the agent that has decided that this process should be suspended has made a clear flag that this process is now ready to be executed and back to the main memory, the process will stay in a suspension status. So if a parent process decided that this process should be suspended, a parent process has to decide when exactly this process should be back to the main memory. If the operating system makes a decision, then the operating system itself will decide when the process should move or return back to the main memory for execution. So in order for the operating system and the process manager to manage all of these behaviors, there is a general instruction for some control tables that has to be maintained all the time to manage the memory, the devices, the files, and the processes. What I would like to share with you today is the primary process tables and the process images. In addition to some other tables, we call them control tables, that definitely would have to be created for the operating system to keep track of the availability of memory, the I/O table that saves the I/O request all the time, also the file tables that manage files. So as you can see, processes, when we have processes, multi-processes in the system, we are creating what we call process table that contains information about the process control blocks of each process individually into a table. So we save all the process control blocks. We call it in total process image. In a process image, we have the process control block plus other information that is related to other piece of management in the system in what we call process image. Each process image is saved into the primary process table, and it is the criteria selected by the operating system of managing those processes based on the order of arrivals, as well as the execution properties and behaviors of each process. So in addition to the process management, as you can clearly see that there is also memory management that has to be done, file management and device management. In order for the operating system to provide well management between the different type of tables, there has been a manipulation and criteria of jumping and accessing between those tables, starting from the memory table. What information do we save in the memory table? We keep kind of information that help in keeping tracking between the secondary device, the hard disk, and the memory. From now on, we will talk about the hard drive as a secondary memory. Sometimes we call it virtual memory. Also, we keep information related to allocation of main memory to processes. We keep information related to the allocation of the secondary memory or the hard drive to processes. We also add information about the protection attribute of blocks, whether it's main or virtual memory. We also need to add information related to manage the virtual memory, the size, the access, the protocol of access. Processes are maintained on a secondary memory using some sort of virtual memory, or what we call it the swapping mechanism, as we previously talked. So is it this the only table that is created? No, we also keep tracking with what we call I/O table. If there's an I/O request, the operating system should create some other data structures that we can save information about the I/O request itself. Means we have to keep track of the status of the operating system, the I/O operation as requested by the process. We have also to keep track of the location in the main memory of the process before sending the I/O request, because if we decided to move the process into the virtual memory because it's blocked, we still need to keep information about the address of the memory of this process when it was moved out. So at any given time, I/O device may be available or assigned to a particular process, and the I/O table has to be updated with such information. Finally, we also need to keep track of file tables. So we are now dealing with processes, files, devices, and memory. The process manager would have access to all of these tables, definitely. Other managers would have access to those tables, yes, except how the communication takes place between the other managers, including the process manager. What information do we save in the file table? We might see the location on the secondary memory, like where this file is stored, the name of the file, the current status of the files, and other attributes that is related to the files on the hard drive. Primarily, when we have file tables, we are talking about the virtual memory. We're not talking about the main memory anymore, because all the files will be saved into the secondary storage. So information may be maintained and used by a file management system as part of the operating system. If you recall before, we talked about user interface, we talked about kernel, which contains all the manager, and we talked about the file management system itself. So a file management system is a crucial component of an operating system that provide good management of files. In other operating systems, in particular that are Windows, that are Unix related, much of the details of the file management system is managed by the operating system itself, not as a separate component. So when we talk about process tables that store information about the processes, the status, the process control block, the process image, the attributes, it's very mandatory to maintain such tables once a process is created, because it helps the operating system to keep track of all the status of the processes, including the attributes about the process, where the process is in the memory, the assigned allocation in terms of the instructions assigned to the process, and it has to be maintained. The process table has to be maintained to manage the execution of the processes. Also, the information in the process table help in identifying the references to memory, I/O devices, and files, whether it's directly or indirectly. Those tables must be accessible by the operating system and also must be accessible to a memory management module. So in summary, guys, what we have discussed today, we have went over a background on processes and processes control block. We talked about the 2-state model. We talked about the 5-state model. We talked about the 6-state model and the 7-state model. We talked about the creation and determination of the processes. What I would like to share with you in the next class is, if we talk about processes, what would be the difference between a process and a thread? And if we're allowing a multi-process system, would this be different if we allow a multi-threading system? And how the management would work to align for process management and thread management. I'm going to stop the recording here and welcome any questions that you may have.